Well, tonight I want to talk to you about the topic climate modeling of the post-flood ice age. This is basically a general report that I gave at the International Conference on Creationism in Pittsburgh 2 years ago, or in 2013 in August. But I've spiffed it up a little bit, and hopefully you'll enjoy it. This is a report of about the last 5 years of my research career at the Institute for Creation Research. I really appreciated the opportunity to lead the RATE project dealing with the radioisotopes in the age of the Earth. That was a very significant project, and there was 8 of us involved in that, and I was kind of the administrator for it. So I didn't really function as a scientist per se. I functioned as a science administrator. And I'm not going to go into the details of that, but I just say that to lead up to the fact that the last 5 years of my time at the Institute, I was able to focus on research in my own specialty. My training was in atmospheric science from Colorado State University. And it took me a while to kind of get my feet on the ground. When you're trained in the university system, you are automatically trained in evolution and long ages and so on. So when I became a young Earth creationist partway through my graduate program, I just didn't become a young Earth researcher immediately. It took me maybe 10 years to kind of get my head together to figure out how to do that, so I was actually thinking biblically. And so the last 5 years, I got to go back and work in my specialty in what I call paleoclimatology. Now that means, it's a fancy word, it just means old climates, but not in the terms of millions or billions of years, it means thousands of years. In the biblical time frame, what happened just prior to the flood, during the flood, and after the flood. So I've done a lot of work in that area, and this last 5 years, I did some things that were very helpful to express what I think happened following the Genesis flood. So in 2008, I proposed that, and I did this at the International Conference on Creationism again, it was kind of a research proposal, that we had the opportunity with the computer power that we had these days to be able to do some significant research modeling using a model that was developed at the National Center for Atmospheric Research. And I proposed that we get the hardware, that's computer power, and the software and the data to be able to do some modeling of weather, of the winter climate and formation of glaciers in Yosemite National Park. And I recommended that we use a program called MM5, which basically means a mesoscale meteorology model. But by the time we got around to starting the project, a newer version had come out called WRF, which was also developed at, I'll say, NCAR, National Center for Atmospheric Research. I'll just use that term, NCAR. And it was basically an upgraded version of that earlier model. So that's the one we actually used. And it was the basic concept here was that we were going to put in different initial conditions that were likely present following the Genesis flood. And the conditions that were significantly different were that the ocean was much warmer than it is today. This was suggested by Mike Ord, who many of you probably heard from Montana, who's spoken over here. He went to school at the University of Washington and has spoken over here quite often. But he recommended, or has said basically, and justified, that following the Genesis flood, because of all the energy released in geological processes and various other activities, such as a possible collapse of a canopy and so on, that the oceans were left much, much warmer than they are today. And then I further said that in a paper that was published by Austin and others, and I was one of the co-authors on that in 1994. And we basically said that the Genesis flood heated the ocean, producing this gigantic El Nino effect. You've heard of El Nino. It's about every 7 to 10 years. There's a wave of warm ocean water that sweeps from west to east in the Pacific. And because the ocean is 2 or 3 degrees warmer, there's more evaporation, more water vapor available in the atmosphere, which serves as the fuel to energize storms and thunderstorms and winter precipitation in the mountains and snow and so on. But if the flood heated the ocean as much as we think it did, it may have been as much as 40 degrees Fahrenheit warmer than what we know of today at the surface. Now, that's a big, big difference. That's why I call it the giant El Nino effect. Well, here I'm using centigrade, so 20 degrees centigrade is about 40 degrees Fahrenheit. And I published, let's see, 1, 2, 3, 4, 5, 6, 7 scientific papers in the Answers in Genesis Research Journal online, which is a free journal. So if you really get into science and you want to see the details of what I'm saying tonight, you can get on the Answers Research Journal in 2010, 11, and 12, and then the International Conference in 2013, and read the reports about what we found. And we had done simulations on over a dozen different storms in various areas. We started in Yosemite, we went to Yellowstone, we went to hurricanes down in Florida, and typhoons over in Saudi Arabia, and hurricanes down in, well, I already said hurricanes in Florida, nor'easters up the east coast of the United States. I'm going to report on that tonight and hopefully help you to see what we found. Well, first of all, I just said this. We did these storms in Yosemite and Yellowstone, in the Arabian Sea, and in Florida, and nor'easters. Okay, now here's the basic idea behind this. Let me pull out my trusty laser pointer here. This is I need to invest in a better laser. I need to get one of those green ones that has a big green spot, but you'll have to bear with me here. This is a Mercator projection of the whole globe. You can see in North America, South America, Africa, Europe, Asia, and Australia here. This is actually South America here, and Greenland up here. In the middle of the oceans, which generally are relatively dark blue, you'll see these light regions. And down through the Atlantic, for example, near Iceland, down through between the North American, South American, African, and Europe continents. What that is a mountain chain that's on the bottom of the ocean, made out of basalt. This was discovered in the 60s by looking at Doppler radar from the sea surface down to the bottom of the ocean, and we discovered, I'm talking about science in general, not creationists, but we discovered these mountain chains that extended all the way around the globe. And this is a 40,000 mile long mountain chain, in some places 6,000 feet high off the ocean floor and hundreds of miles wide. And it was formed as the continental plates separated and the hot magma from deep in the crust and in the mantle came up and flowed out on the bottom of the oceans and solidified as it cooled, forming basalt mountains. And as you can imagine, that hot basalt, which is a tremendous amount of material, would release a lot of heat and warm the ocean. So that is the primary source for the heat, we believe, that warmed the oceans. And by the way, I might mention, this is not just hypothetical. It turns out that there has been, for the last 40 or almost 50 years now, several ocean drilling programs, one called the Ocean Drilling Project, I forgot what the one before that was, in which they had ships geared with drills on top of the ship, and they would drill down through, they would send their drills down in the bottom of the ocean and drill down into the seafloor, and they were able to find out in that sediment on the bottom evidence for how warm the oceans were in the past. And they were able to calculate that the oceans were as warm as 40 degrees Fahrenheit warmer than they are today. Now, you could say, okay, if that material, that basalt came out over millions of years, it would heat the oceans and it would not get real hot. But if, in fact, the Earth is young, on the order of thousands of years, and this material came up rapidly over such a short time, you would have tremendous amount of heating to the point that the oceans would have warmed greatly. Now, the conventional scientific community says, yes, the oceans did get that hot, but that happened over millions of years, and it's no big deal. And in fact, when the dinosaurs were on the Earth, they say some 65 to 100 million years ago, the oceans were that hot. But we're saying that it happened just a few thousand years ago, and then the ocean temperature has cooled down to what it is today. Well, what would the climate have been like with the oceans that warm for a few hundred years after the Genesis flood, if that was the case? So that's what we wanted to model. We ended up using conventional climate models that were developed at the National Center for Atmospheric Research, used them as they were, used them on actual data for storms that we have today to make sure that they would duplicate the conditions that we observed here in these storms, like hurricanes going across Florida, their path, how intense they got, and so on. And we were able to do that very easily, but then we changed the sea surface temperature to see what would happen. And everything changed. The hurricanes got extremely strong. They produced incredible amounts of precipitation, high winds. The storms that came in over the continents, for example, into Yosemite and the Sierras, into Yellowstone, across the Cascades, and into the northern Rockies, they produced incredible amounts of precipitation. Now, I'll give you the details of that in a moment, but let me give you just a little more information about where these mid-ocean ridges, as they're called, were located. The mid-ocean ridge here comes down from Iceland, down through the North Atlantic, the South Atlantic, into the South Atlantic, and then continues across the Indian Ocean to go south of Australia. You know, over here you can see where it continues and comes south of Australia, out into the Pacific Ocean, and then back up to the Baja in near off the coast of Mexico. Well, there's a couple of other places where that's rather interesting. There was a branch right here in the Indian Ocean that went north into the Arabian Sea and into the Red Sea, actually up into this area a little bit. Now, not only were the oceans in general very warm, but close to where these mid-ocean ridges, you'd expect it to be even warmer. So one of the things I got most excited about, and I'm really excited to tell you about in this talk, is I had wondered about what would happen in the Middle East if we had a mid-ocean ridge in the Arabian Sea very close to Saudi Arabia and Israel and the Middle East here. What would happen in that region right there? So I wanted to simulate that, and I'll get to that in a moment. Okay, let's start. I'm going to have 5 basic domains where we did our simulations. We had, as I said, over a dozen storms we simulated. It's 2 to 3 or 4 in each domain. The first domain we looked at was in Yosemite. So our model, our WRF, our Weather Research Forecast Model, had a domain. That means that it looked at data in this giant area covering the southwestern United States. Here's the Central Valley of California, Coastal Range, and the Sierra Nevada. Yosemite is right in the Sierra Nevada here, and Mount Hoffman is right in the middle of Yosemite National Park. And there's a line here, you'll notice, I have some diagrams of where the precipitation occurred along a particular line to show you how the mountains affected the flow of air across the continents and how it produced the precipitation on the continents. So let's look at that. Okay, first of all, let me give you some eye candy here. If you haven't been to Yosemite, or if you have, it's always a joy to be able to see it again. This is Half Dome in Yosemite, which is one of my favorite spots. I never got up there, but my son climbed to the top of that one day. But this is a rather significant spot in Yosemite because there were glaciers that covered this whole area in Yosemite up to about here on Half Dome. In fact, we know that because there are what are called striations. That's where the ice, as it moved from a higher elevation in the background here, downhill past Half Dome, it scratched the rock, leaving what are called striations in the rock. And from about here upward, there were no striations. From about there below, there were. Now, I'm standing over on Glacier Point, which is just west of Half Dome, and Glacier Point was covered by the glaciers. As the glaciers came down from the higher elevation, they passed down a valley to the north of Half Dome and to the south. Here you can see some of those pictures. Here's the valley to the north of Half Dome. So the glaciers up in this area covered the mountains and then came down through here, grinding out the glaciers, leaving, well, in fact, let me show you the next picture. This is the valley to the right of Half Dome. Half Dome is over here. This is the valley in here. And as the ice came down, it ground off the rock, leaving these vertical walls and leaving what are called hanging waterfalls. So as the water is coming down off the mountains today, it reaches a spot where the ice ground off the rock and left a vertical cliff. So that's why there are so many waterfalls in Yosemite. Okay, here's another view from to the northeast of Half Dome, looking back toward Half Dome. That's Half Dome there. A moment ago, we were over in this area here looking up this valley on the north side of Half Dome. Here we're up in the park looking southwest down past Half Dome. You notice there's very little vegetation, almost no vegetation, just a few trees left. There's no topsoil. Those glaciers completely scraped off the topsoil and left the granite exposed. Now, Andrew Snelling and I went on a trip with our wives to Yellowstone, or to Yosemite, to collect rock samples for the RATE project. This is one of my favorite experiences, and I don't have time to get into that. But it was easy to collect rock samples there in the park. But by the way, you have to get permission for. Don't go to the park and pick up rocks; you'll get arrested. But we did it for research, and it's really a fun thing to do. Now, here's another spot in Yosemite. This is in Tuolumne Meadows, and over here you can see where the glaciers had ground down the rock on top of some of the peaks. This is near Castle Peak. I forget the name of that one there. That's what's called a horn, where the glaciers have chipped off the rock. And the glaciers came down this valley, flattened it out, and you'll see here where it actually came over some domes of glacier. This is forgot the name of the spot here, but there was glaciers coming down from this direction going over there and grinding off that as they went downhill in Yosemite. Here's a valley that was filled with a glacier at one time. It's actually called after Lyell. It's Lyell Valley. If you remember Lyell, he was one of the motivations for Darwin to change from a biblical view to a long-age evolutionary view when he did his trip on the Beagle. And so Lyell had written a book in geology which affected Darwin. So the evolutionary geologists decided to name this valley after Lyell. Okay, here's another, now when these glaciers come down, quite often they leave moraines behind, so you know they've been there. This is on the east side of the Sierra as you're going down toward Mono Lake. Here we're actually looking up the valley toward Tuolumne Meadows, and the road that goes over the pass and down into Nevada, or actually down toward Mono Lake. When you take that road down there, you don't really notice to the side these big moraines. Now, the moraines are material that's left behind by a moving glacier. You have the big one over here, and you have another little one over here, and all along here. And the glacier came down and kind of stopped right here, and then when it melted back, it left all that material. Well, we know about that because we have all kinds of moraines around here. In fact, Seattle SeaTac Airport is sitting right on top of a north-south oriented moraine that was produced by glaciers coming down from Canada. Okay, well, that's kind of a trip through geology, but here's some of the results of the simulations. Now, this is a little bit, maybe a little harder for you to see. I can't see it on my screen at all. I have to look up here. What this is accumulated precipitation for a storm, which we even call today the Pineapple Express. You know, these are storms that come off the Pacific from near Hawaii. They have their source region there where it's relatively warm air. As the wind and the storm comes across from the South Pacific near Hawaii, you swear you can smell pineapples in the air, right? Or bananas, maybe. But it's bringing a lot of water vapor. And when it hits the Sierras, it dumps like crazy. I was the director of a government project for doing cloud seeding in the Sierra back in the 70s. And we got there we started the project in 1977, and it was like a 4 or 5 year drought where all the reservoirs were empty. It's very much like what they're experiencing right now. And when we started the project, it was a research project, but within 2 years after we started the project, one of these Pineapple Express storms came through, and it dumped 30 feet of snow in one storm. The reservoirs were filled in 1 year. And there was a Pineapple Express, one storm right after another. So you can get a tremendous amount of precipitation when you have this moisture-laden air coming from the South Pacific where it's warm, if the conditions are right. Now, what we did was, let's assume that the oceans were warm all over right after the flood. What would happen? Now, the normal condition like we have today, these are temperatures, the sea surface temperature here in degrees centigrade. That was at 0 degrees centigrade, which is, relatively cold, obviously. It's too cold because it would be freezing or almost freezing. And in 10 degrees increments up to 45 degrees centigrade warmer. That would be 90 degrees Fahrenheit, which is really warm. That's like bathtub water. Now, it's probably unlikely that it got quite that warm, but it's not impossible. But so we looked at what would happen in terms of precipitation. Let's assume that it was 45 degrees centigrade. That's 90 degrees Fahrenheit or thereabouts, 86 actually. Right on the peak of the Sierra, right near Mount Hoffman, which is where we centered our simulation, which is one of the highest peaks in Yosemite, it produced from this one storm over 3,000 millimeters of precipitation. Now that's 3 meters of precipitation, or about 9 feet of water. Not snow, water. So if you got 9 feet of water and it's in snow form, that's about 45 feet of snow from one storm. Now, you can have multiple storms, and if you have those year after year, which we think happened right after the flood, you can see how you could accumulate glaciers very, very rapidly. In fact, I'll anticipate one of the conclusions we made from this project was that we can accumulate all the glaciers and ice sheets on the Earth from this kind of a condition in less than 500 years. It didn't take 100,000 years for all that ice to accumulate. It could happen in less than 500 years if the oceans were warm, which we believe they were for several hundred years after the flood. Okay, now this I didn't describe here. This is the amount of precipitation. The horizontal axis is the distance from Mount Hoffman. This is 45 degrees southwest, so that's like 1,500 meters. This would be like near the Sierra, out off the coast. This is the Sierra Nevada, and then this is inland further up to the northeast of Yosemite, out in Nevada and into Utah. So there's mountain ranges, all those places. So that's where it's called orographic precipitation. It's produced by the orography as the air flows over and it dumps on the various mountains, so you get more snow, more rain on top of the mountains. Okay, I'm going to go a little faster for some of the other diagrams. This is a different type of storm. The other one was the Pineapple Express, which was very moist. This is what's called a deep upper low storm. This would be like one that comes down from Canada or down from the Gulf of Alaska, and it would produce not as much precipitation, but it would produce a significant amount. In fact, here you can see it's on the order of, if you had 50 degrees centigrade, it would be 2 meters of precipitation, or that's 12 feet of water, or about 6, 2 meters would be 6 feet of water, or about 30 feet of snow. Now that maybe if you're not happy with that hot a temperature, you can look at some of the other temperatures down here. And so depending on how many storms you get per year and which kind of storm, you can get the type of precipitation. Okay, we're going to go on to a different domain now. This is the domain in Yellowstone National Park. Here you see up in the north area, rocky around northwestern Wyoming is where Yellowstone National Park is. And we centered that domain on Yellowstone Lake Lodge, which I'll show you close up in a moment. But again, we have an orientation of a 45-degree angle here along the topography, so you could see what the precipitation would look like along that line. So we did a similar type study. Here's a little more detail about Yellowstone. If you haven't been to Yellowstone National Park, it's an absolutely gorgeous place to go. You got Yellowstone Lake in the middle. Lake Village is right up in the northwest corner, and that's where the Yellowstone Lodge was, which we centered our simulation on. This little round spot in the middle is a caldera for the Yellowstone volcano, which erupted. It was one of the largest volcanoes on Earth, if not the largest. This whole thing was erupted and then settled back down, and the edge of the caldera is about 30 miles in diameter. So it's like looking into Mount St. Helens, except it was not as up on a mountain so much, and it didn't have one wall completely out of it. Although this did have there was a break through the north wall of the caldera, so that water in Lake Yellowstone flowed north and through the wall, and this is Yellowstone River that runs down out of the park and into Montana. Here's Old Faithful, which you're familiar with, Madison Junction, and there are 5 different entrances to the park and mountains all over that. Now, there's another significant thing, and that is that right through the middle of Yellowstone National Park is the Continental Divide. It runs right up through here and across and out the other side of the park. So this is a high location in the Rocky Mountains, and so when you have this precipitation coming up, it forms these glaciers at high spots and then flows out in all directions. For example, I need to go back here and show one other thing first. There's 2 significant mountains here that you need to be aware of. One is Mount Sheridan, which is here on the south end of the park, and the other one is Mount Washburn. Those are 2 of the highest mountains in the park, so that when the glaciers formed, you'll see here, the glacier tended to center right over the park, right on top of the Continental Divide, and then glaciers flowed out from there all directions. For example, it flowed down the Yellowstone River and up toward Livingston, Montana. It flowed down to the south in front of the Tetons. Here's Jackson Lake, so that the glaciers were flowing south out of here down the Snake River. The Snake River has its head, or the headwaters, in Yellowstone National Park, and flows down through the front of the Tetons and then goes west and flows into the Columbia out near the Tri-Cities area. Anyway, the glaciers are incredible in Yellowstone National Park. Now here's the 2 mountains I was telling you about. This is hard to believe, but we have evidence that the glaciers almost covered Mount Washburn and did cover Mount Sheridan, and the actual lake level is about 8,000 feet above sea level, and the glacier could have gotten as much as over 11,000 feet high. So you had a glacier that was like 3,000 feet thick on the top of Yellowstone National Park. Now that's an actual case. Now the question is, how did it get there? We believe from our simulations we can show that this happened because the Pacific Ocean was warm, brought all that moisture in and dumped it very rapidly into Yellowstone. Okay, here's another feature or 2 that you might enjoy. This is where the Yellowstone River is coming out of the caldera and the Yellowstone Falls flowing downhill in the northwest corner of the park. Here's the Tetons. This is a tour group that ICR took to Yellowstone. We took probably a half a dozen tours there. Wouldn't you like to go with this group? That was just a gorgeous tour. And we put this group in front of the Tetons, and these mountains were covered with glaciers, and even today there are still small glaciers still up in there that come down. here's one at Jenny Lake, which used to be filled with a glacier. And the group was standing in this spot right here on the end moraine where the glacier came down this valley and stopped here. And when it melted back, it left the debris here, which formed a natural dam. So Jenny Lake is the result of a glacier. Okay, now here's the simulation. This is for the one type of storm that I simulated. We simulated probably half a dozen different storms. A Gulf of Alaska low came in. Yeah, you can't barely, I can't even see it myself. I'm sorry. I thought this would project a little bigger, but it doesn't. Again, it was centered on the Lake Lodge, Yellowstone Lake Lodge. That's the 0 spot. Goes to the northeast here, to the southwest there. You see right on the Lake Lodge area is where the heaviest precipitation occurred, but there was also some to the southwest, because this is the Sierra Nevada off to the southwest. So there was a lot of precipitation that fell at the various mountain ranges as it approached there. Then you go to the northeast of Yellowstone, that basically the mountains are disappearing there, so you don't see much precipitation out that way. Okay, another domain, and this is the one I'm most excited about. This one I did near the end of my project, and it got so exciting. The domain was in Saudi Arabia. We picked a spot right in the middle of Saudi Arabia, and here you get to learn a little geography at the same time. If you have heard all these names, but you don't know quite where they are, let me kind of repeat them for you. Here's the Mediterranean over here. This is the boot of Italy, Greece, and Turkey. Israel's here. Here's Egypt. This is the Red Sea that goes down into the Arabian Sea. And Saudi Arabia is a peninsula right in the middle of this area. In Africa, south of Egypt is Sudan, Ethiopia, and Somalia. On Saudi Arabia, you've got Yemen, Oman, the United Arab Emirates, and this is the Persian Gulf where we have all the activity these days. This is Iraq, right to the east, and of course Syria's up in here. I didn't put it in, but Israel, Iraq, and Syria would be here. This is Iran, Afghanistan, and Pakistan over here. And of course, here's the Himalayas, which is very high terrain. Okay, so we were simulating this. Now, the reason I was simulating, I told you earlier that the mid-ocean ridges that produced all this tremendous heat came right up into the Arabian Sea and then turned right up into the Red Sea. So you would expect this whole area to be very hot. Now, we know that warm sea surface temperatures amplify or accelerate hurricanes. Now, a hurricane in the area over here in the Arabian Sea is called a typhoon. And off the coast of Japan and China, those are all typhoons. It's the same kind of storm, it's just that it's got a different name. But we know that when you have a warm sea surface temperature, it amplifies the storm, makes it get stronger, has more circulation, has stronger winds, more precipitation, and does a lot more damage, more storm surge, all kinds of things. So can you imagine what the hurricanes were likely, or typhoons were very like right after the Genesis flood, if it was much hotter than it is today? Well, my thought was maybe this explains some scripture where it gives you the impression that Israel was a land flowing with milk and honey. And the Jordan River, you could see from the north end southward, and you could see it was green as far south as Zoar talks about that. Well, my thought initially was, well, maybe a warm ocean would cause these storms to get bigger, last longer, produce more precipitation. Well, I was wrong. It turns out it does much more than that. It does that, but it does something more significant, and I'll show you in just a moment. Today, when you go to the Middle East, what do you see? This is the kind of land that you see. Very little vegetation, basically desert. It's even worse than Nevada. And you look up, this one here is like looking down from the Jordan River up some of the slopes west of Jerusalem. Very, very dry and desolate looking. If you get out into the deserts in Africa or Saudi Arabia, there are a few places where you have oases, but that's underground water that's seeped there, but generally it's just sand everywhere. But we have the impression, maybe from Scripture, that it was much moister in the past, more vegetation. Now today, there are a few places in Israel where it's not so dry. For example, this is on the west side of Jerusalem as the terrain goes up toward the ridge at Jerusalem, and there's more precipitation as the air comes off the Mediterranean, and it produces trees and plants. But even there, it's only that way for a very short time, except for the trees. It's very beautiful. If you want to go to Israel, go in March or April, and you'll see flowers and beautiful vegetation, but it doesn't last very long. It's like going to the desert down near Palm Springs. It's only good for about a month or less. Well, my thought was maybe this warm ocean did something significant. So let's, first of all, take a look at the mechanics of a hurricane so we understand them a little bit better. A hurricane basically is a swirling mass of air, and it gets started out in the ocean when there is a warm spot in the ocean and the wind comes in a certain way that it produces some convection. The convection starts to rise, and on a rotating Earth, it causes the air, as it starts to circulate, to move toward the middle and then rise up through the convection and then flow out at the top in the other direction. So down at the bottom, you have a counterclockwise circulation. It goes around counterclockwise. And up at the top, the circulation is clockwise. And in the middle, between the two, you have air flowing up, and as it goes around, it's flowing up between the surface and a loft. And it's cold up here where there's ice. Down to bottom, it's very warm. Right in the middle is something called an eye, and this is kind of a return flow. As the air goes up here, it can't all escape out this way. Some of it goes in and goes down, and air, as it's going down, will dry out the moisture, get rid of the clouds, and reduce the precipitation. So that when you're on an airplane or a satellite looking down on a hurricane, you can actually see all the way down to the surface in many cases, right down to the ocean. So that's why you have the eye, and you can track where the middle of the storm is by following that. Now, here was a storm in the Arabian Sea a number of years ago. I've forgotten what year it was now, but this is called Gonu, and it was a fairly sizable typhoon. And it was forecast and simulated by the Meteorological Office in the United Arab Emirates. They used the same model that I did to be able to forecast. This is the most popular forecast model in the world today, the weather and research forecast model. So we wanted to look at Gonu, and here was the track of Gonu. This is the precipitation it produced as it came across the Arabian Sea, and it hit the Gulf of Oman. It actually glanced the tip of Oman here, crossed the Gulf, and into Iran. Notice it's Iran there. And you'll notice how much precipitation it produced. It produced 250 millimeters. That's 1/4 of a meter. That's a little less than a foot. Let's see. Yeah, a little less than a foot of rain or precipitation as it moved across in any one spot. And then when it get into Iran, it hit some mountains there and produced quite a bit, and then it kind of died out. Well, then it went away. Well, the question is, what would happen if you had warm ocean and it lasted for dozens or hundreds of years? So we simulated it with this forecast model, and we got the following situation. We get produced, not only, I need to say one other thing. We simulated Gonu, and we were able to simulate the actual occurrence and the track and the precipitation of the actual storm. Then we increased the ocean temperature, both the Mediterranean and the Arabian Sea, made it all warm, and things changed dramatically. The hurricane or the typhoon didn't just produce a certain amount of precipitation and then die out. A change happened in the general circulation of the whole atmosphere. It developed a large circulation over this whole domain. Now here's the Saudi Arabian Peninsula, right in here. Right in the middle is the middle of Saudi Arabia. That's the Persian Gulf. Here's the Red Sea in here. Persian Gulf is right here. So we got a circulation. What this is the wind at 5 kilometers, or about 15,000 to 18,000 feet above sea level, and it's what we call a hypercane. This is even bigger than Gonu was, and it produced wind speeds in some places as high as 132 meters a second. That's over 250 knots. 250 knots at that altitude. And you got these little circulations which were like a typhoon, and embedded in that was this bigger circulation that continued to rotate. And in that situation, you not only have high winds, you also have a lot of precipitation. So here's the precipitation that developed from about 3 weeks of this simulation in very, very warm surface conditions. We got over 300 inches of rain out here in the Arabian Sea. We got 15 inches of rain over the entire Saudi Arabian Peninsula, and places up in the eastern Mediterranean, 40 inches of rain. So we had a tremendous, over a 3-week period, we had a tremendous amount of precipitation. Now, this wouldn't have been a one-time thing if it was after the Genesis flood where the ocean was warm. It would have kept doing this, continue. So even out in the middle of the desert, you would have lots of precipitation. Okay, here's an animation of this hypercyclone Gonu, as we call it. And here you'll be able to see the development of some of the circulation. You can't see the boundaries of the continents, but here's Gonu. As it developed, it got very strong. It went across Oman, Hypercane Gonu, went into Iran. There was another circulation that developed up here in the Mediterranean and worked its way down over Egypt. And you notice all these little patterns in here. That's high wind speed forming in this circulation. In a moment, you'll see there's a little circulation forming up here. Over this 3-week period, it just kept producing this giant circulation centered on Saudi Arabia. I think there's another one develops up here here it is in North Egypt. Well, where'd it go? Here it's developing now. Okay, it's a little circulation that's over the Mediterranean because that's warm water, and it continued to do this circulation. Here it's coming down through Egypt, down along the Red Sea, and all that circulation. So underneath this very strong wind speed, you get vertical motion and a lot of precipitation. Okay, this is a bit fast, but I want to give you the impression. Okay, now this one's a little more fun to follow. I actually did this simulation before we got into Saudi Arabia. I wanted to do a simulation of a very small hurricane. It wasn't even a hurricane, it was just a tropical storm in the Gulf of Mexico, to see if the warm surface that I assumed would produce a large hurricane. In fact, it did. It produced a hypercane, as we're calling them. Initially, Hurricane Florence was into Mexico. It was a minor hurricane. We assumed a sea surface temperature of 45 degrees centigrade. That's about 90 degrees Fahrenheit. It grew to a hypercane in 24 hours. It filled the entire Gulf of Mexico. The horizontal and vertical wind speeds doubled over the actual Hurricane Florence, and precipitation increased by a factor of 10 from what the actual hurricane did. Now, here's the simulation. We start with a hot spot that I assumed was over the middle of the Gulf of Mexico. This is the Gulf of Mexico here. This is Mexico. Right away, you begin to get convection. The green area is rain, the yellow area is cloud. These intervals are 1-hour intervals. And the storm filled the entire Gulf of Mexico, 1,000 kilometers wide, over 50 kilometers high, and the precipitation was 10 times what actual Florence did. Okay, a couple more domains, and then I want to make some general conclusions. We did some simulations in Florida from some hurricanes that occurred down there. One of them was Hurricane Charlie. Maybe you heard of Hurricane Charlie. The reason I selected this one ran over a friend of mine's house. You remember Dr. Gary Parker? Have you ever heard of Gary Parker? He lives still in Punta Gorda, Florida, and this Hurricane Charlie came over and practically destroyed his house. He had to have lots of it rebuilt. So I chose to pick that one. It wasn't a gigantic hurricane, but we simulated it. This is the domain over the South Florida and the Caribbean. And here's a picture of that same area, kind of give you a little flavor. That's such a beautiful satellite picture, I had to include it. Of course, I had to include some oranges. some alligators, maybe a marina or two, a sunset. Okay, anyway. Okay, here's a simulation of Hurricane Charlie with a warm Atlantic Ocean and a warm Gulf of Mexico and a warm Caribbean. You can't see this here, but Florida's down in here, and the Hurricane Charlie actually came right across and up and formed a gigantic circulation off the east coast of the United States. And it ended up off the east coast of Boston, or Washington, D.C. area, and because of such a temperature contrast between the continent and the ocean, you ended up with this gigantic circulation up here. It started off as just a little hurricane and became a hypercane, very much like a nor'easter, but it was a hurricane. Okay, I'm going to go on. Here's what the circulation, let's see what happened there. Yeah, okay. Here's what this, just a slide of that circulation. It showed that the circulation was very strong from the southwest off the east coast and return flow back down along the east coast in this racetrack pattern. You produced a gigantic circulation all over the eastern United States. Here's Louisiana, Arkansas, Missouri. So the whole eastern United States is covered by this circulation when you have such a big temperature over the ocean. Okay, now here's some of the tracks. It turns out that when you have very warm ocean temperatures, it changes the track of the hurricanes as well. Here is the Hurricane Charlie. The actual observed hurricane was the X's. My simulated hurricane, where I used the actual temperature of today. And you can see where the track of Hurricane Charlie went across up over Florida along the east coast. My simulated hurricane, with the temperatures that we had during that occasion, it followed it fairly closely, a little bit offset, but up the same path. But the hypercane, where we had warm temperatures, let's see, it doesn't say here what the temperature was, but it was probably 40 or 45 degrees centigrade. So the hypercane came up to a certain point and then zapped up the east coast and then did a little circle up here. If you remember, we had this gigantic circulation, so the hurricane was forced, instead of coming this way, it was forced to kind of go a more easterly track and get involved in that circulation there. We did another one called Hurricane Faye, which is a very weak hurricane. It did a similar thing. Again, the X is the observed path. Here it goes here. Faye went up here and over into Louisiana. The simulated one followed along pretty well until we got to about here, and then it went on up east. So my simulation didn't follow it near the end of the simulation very well, but the hypercane was incredible what it did. It followed along until it got stronger and stronger, and then it went over into the Gulf of Mexico where there was a big pool of hot water, and it just stayed over there. But then there was a second circulation that developed, so I got a hypercane over here as well. So this whole thing became very chaotic under very hot conditions. Okay, one last domain, and this is nor'easters. Has anybody ever lived in the Northeast and heard about nor'easters? You know how much damage they can do with all the snow. Well, we selected a spot. The domain was this whole area centered on Washington, D.C., because Washington tends to get affected by that a lot. Let me give you a little more idea behind how this works. If you have, and we believe this happened right after the Genesis flood, that the continents became very cold and the oceans were very warm, so that you had a big temperature contrast, hot to cold, along the coastlines. So if you had a little circulation that formed down here, it tended to ride up along that temperature contrast line and form very strong nor'easters. Here's how a nor'easter works. You've got a cold front with a low pressure center that may start down in Florida or somewhere and runs right along the coast. The circulation at the surface around that nor'easter is ahead of the cold front. It's bringing warm, moist air off the ocean, rising up over a warm front, and dumping snow in the northern part of it onto the continent, and then sweeping back down again this way. When you have a hypercane, it becomes so large it can affect the whole eastern United States, not just along the coast itself, But you can see how you could contribute to the formation of a ice sheet over the whole eastern U.S. Here's looking from south to north along a nor'easter. Here's the ocean. Air is being brought over up the front and dumped as snow on the north and west side of the hurricane. Here's what the effect is in Washington, D.C. And I believe what happened after the Genesis flood, you had these nor'easters that were amplified, and they were probably happening every 2 or 3 days, all winter long, possibly even during the summer. And the summers were cold enough that the snow never melted. It just kept accumulating and getting deeper and deeper and forming glaciers. I think I'm going to skip over this. You've probably seen enough of these things. But there is one thing about this particular simulation that gives us some warning that maybe the simulation needs to be redone because we had a little challenge. Most of the precipitation in the, for example, one of the simulations was a 2007 St. Patrick's Day nor'easter with a very warm ocean. It tended to draw the precipitation and the activity off the coast rather than along the coast and onto the continent. So we may need to have someone redo some of those simulations. Okay, here's some of the results, and I think this is putting all this together. The wind speed and precipitation increased in all the simulations that we did when we increased the surface temperature of the oceans. Generally, the increase in precipitation, believe it or not, was between 500% and 2,000%. In other words, 5 to 20 times more precipitation out of these storms, whether it was a mountain storm or a hurricane, typhoon, nor'easter, whatever. It increased the precipitation dramatically. The 3,000-foot glaciers in the mountains and the ice sheets on the flatland, we believe, could have developed in less than 500 years. Tropical cyclones became hypercanes. These are gigantic hurricanes. The tracks were significantly altered. Nor'easters were greatly intensified. And regional scale, counterclockwise, low-level circulations developed on the East Coast and in the Middle East. And this, I think, is really neat. Heavier precipitation probably fell over the entire Middle East, giving more vegetation. And by the way, that's more than just some statements in Scripture. People have gone and found evidence that there were trees, large trees that lived out in the desert, and they were not where there was underground water so much. Many of them had died and were still preserved out in the middle of the desert where there wasn't underground water. How did they get there? We think we may have an explanation. Now, this is going to be way too small for you to see, but this is a summary of over a dozen of the simulations we did. You can see this is the increase in precipitation for each one of them, anywhere from about 480% or 500%, I guess there's one that's 400, all the way up to almost 3,000%. That was the increase in precipitation for each storm. Okay, the conclusions. The in-car weather research forecasting model simulated the storms well, and that is the mid-latitude winter storms on the West Coast, the tropical storms in the Arabian Sea and in Florida, and the nor'easters along the East Coast. There were some glitches, but by and large, it did real well. The increased sea surface temperatures we assumed following the flood was the likely cause of the ice age in polar regions and on mountaintops, and the increased vegetation in the Middle East. The heavy snow in the mountains of the western U.S. and the northeast produced glaciers and ice sheets, and more rain in the deserts of the Mideast supported more vegetation for centuries after the flood. Okay, so there's some recommendations here that I made. A few of these simulations need to be rerun to solve a few of the little things that we ran into. We basically feel that the simulation should be run with this forecast model using smaller grid point spacing if storage and runtime limitations can be purchased and somebody can do this. This is a 5-year research effort, by the way. Finally, I need to give acknowledgments to the following people and organizations. The National Oceanographic and Atmospheric Administration, that's the Weather Bureau basically, and NASA provided the weather and satellite data that we used. NCAR, National Center for Atmospheric Research, provided the model we used. The output was displayed by Viz 5D, which is available on the internet. It's a beautiful, beautiful system for displaying data. Wes Brewer was my compatriot in running the model, and he provided the output, which we used to publish. By the way, he's teaching in North Korea now, by the way. It's kind of an interesting situation. A friend of ours, Richard Carpenter, offered some advice on how to use the model. Answers Research Journal gave us permission to use the images, and the project was funded by the National Creationist Research Foundation at ICR. So I'm going to stop there and turn it back to Chris. I understand we're going to have some questions and answers in a little bit, but I'll give it back to Chris right here. Thank you for your attention.
All right, thank you, Dr. Vardiman. So we have time for a couple of few questions. Before we get to that, we want to take just an offering real quick. So if you're prepared to help us tonight with Dr. Vardiman's honorarium, that'd be great. Let me get our guys forward, and then I'll bless the offering with a word of prayer. Again, if you're making out checks, just make those to Cedar Park. The offering's turned over directly to Cedar Park, and who's gracious enough to allow us to use their facility, these kind of things. I mean, there are very few churches that offer these kind of educational programs. You know what I'm saying? So if you're looking for a church home, or, if this is Creation Science's interest for you, that's great, but there are other educational opportunities here that you just really won't find anywhere else. Let me bless the offering and word of prayer. Father, we thank you again for Dr. Vardiman and for allowing him to come and share his research with us this evening. And Father, we just ask that you bless the offering that's taken up today, Father, and the work that will be done with those funds, Father. We again just ask for your blessing on Cedar Park, Father, that you would allow the knowledge of this particular church to reach peoples out there that are still looking for a church home, people that don't know you, Father, that you would allow this congregation to just grow and grow and grow and reach ever more people, Father. Bless the offering that is taken up this evening, Father. We ask these things in Christ's name. Amen. Okay. So as that's going around, we can do some question and answers. If you have a question for Dr. Vardiman, just raise your hand. I'll bring the mic around. And I know there's a bit of a technical talk, but any questions? Everyone's like, wow, that was yes, sir.
I'm not sure how relevant this is to your talk, but one thing I've been looking at just a little bit recently is just dealing with, and not a lot, so I need to dig into this more, but...
Could you speak up just a little?
Yeah, sure. With the, some of the secular scientists give the impression about the ice sheets and having the layers and like hundreds of thousands of years. Did your research address that at all, as far as we have these layers that they say are annual layers? Does this affect that at all, what you came up with?
Yeah, the question is, what about the annual layers that is reported by the conventional community? One of my students looked into that. I looked into it quite a bit too, and at the ICR we had a graduate school for a number of years, and one of my students looked at that specific question. First of all, the layers are definitely there near the top of the glaciers and the ice sheets, particularly in the polar regions. In the mountains where the glaciers are, you don't have very great depth that you can look at, but you can in the ice sheets in the polar regions. The layers get thinner and thinner as you go down further, because as the ice compresses, it makes the layers thinner as they spread out and get very, very thin. And it's legitimate to say that those are annual layers down to a couple, 3,000 years. I don't think that's a problem. But when you go beyond that, they're so thin that it's hard to know for sure whether they're annual or not. And there's all kinds of inconsistencies in it, but they just basically say anytime you see a layer, that has to be annual. One of the things that you can question about that is, it's possible that when the lower layers were being accumulated, they were not annual, that they were actually storm related. And in fact, if you look at how a layer is formed, even today, they say that at the bottom of the layer and at the top of the layer, the conditions were different than they were in the middle of the layer. And you get kind of a crystalline structure, and it introduces bubbles. So you can see those layers of bubbles in there. That's how they get the annual layer. Well, you can get the same thing on an individual storm, particularly if you had a storm every 2 or 3 days, like I suggested for nor'easters. And when you get down further and they've been compressed down, you can't tell whether they were annual or storm related. So that basically is my explanation is why you would get, instead of 250,000 years, you got 250 layers, but they may not all be annual.
Do you have another question? No one wants to try to stump Dr. Vardiman. You were pointing to someone, Dr.
Are there scientists at ICR or some other creation research organization that are still doing some more research on this? And is that getting published in some of the other creation journals?
Well, there's nobody right now that's actually doing the simulations like we did for that 5-year period. That takes people with special knowledge and desire to be able to do that. Generally, right now, I don't know of anybody that's doing that specific type of simulations. There are people that are still looking at the reports that are coming in the conventional literature and critiquing them, but they're not contributing original research that would counter some of the ideas. That's unfortunate, but that one of the things is it's very expensive and it takes a big commitment to actually spend time doing original research. That was why rate, for example, was unique. One of the things that I feel strongly about is that creationists, as a creationist, we need not only criticize the evolutionary model, but we need to develop our own results that would justify the viewpoint that we have.
This is probably a separate seminar question, but how does the interpretation of this data affect your perspective on global warming and perhaps having to do with the layers of glaciers and the accumulation of snow?
I didn't hear that last part completely. What was that last comment?
And how does the interpretation of the data that you have here affect your opinion on global warming with the accumulation of snow and glaciers? Yeah.
Okay, these results don't have a whole lot to do with the global warming issue, but I can just kind of make a quick comment. My own personal viewpoint is that global warming does occur, but it's cyclical. For example, when I was entering graduate school in 1970, the whole community thought we were going into another ice age because we had been having cooling from about 1940 to about 1970. And one of my professors even had the idea of spreading carbon dust all over the North Pole and the South Pole to try to melt the ice so it wouldn't accumulate so much. Well, then starting about 1970, it started warming. So it goes through some cycles. And my personal view is that it's primarily driven by solar effects. And it's a convoluted issue. It isn't just simply that the sun puts out more energy or less energy. It's the way in which it occurs, and it's very, very difficult to evaluate that. But I think there are some people in Denmark that I've been following that I think have begun to get some handle on that. And it's not just an 11-year solar cycle like we're all familiar with. It's a cycle built on top of that may have 50-year or 100-year period. And so we are contributing to global warming to a small degree. I don't think it's the major part, but it's there. It's kind of on top of it. But I'm not one who's overly concerned about our contribution.
All right. One more question. No, we need it.
The magic question about global warming is, has it happened in the last 15 years, or has it been basically static and the old ice hockey stick, all is a bunch of jumble of statistics and everything else? Has it really gotten as warm as they say over the last 15 years? or are we just static?
Well, you've opened a real Pandora's box there. I can't really answer that question in the time frame we got. I'll just say this: two parts to it. There's many parts to it, but two parts I would say. First of all, there was a kind of a concerted effort to make the data look like it was worse than it is, and that's why it's called a hockey stick. It's kind of a flat piece, which is the handle, and suddenly it takes off. There was some manipulation of the data that was not appropriate, and some of the scientists involved in there got their hands slapped over it. So that's part of it. Another issue is that part of that whole effect is due to man's growth and where the weather stations were originally located. For example, many of the initial weather stations that have got long periods of record, like 100 years or so, they were out in the country originally. And as you well or may know, the country tends to stay cooler at night particularly and doesn't get as warm as the daytime. In the city where there's a lot of concrete and asphalt and buildings and so on, it produces what's called the heat island effect, and that causes much more warming. So if you've got a weather station that's been initially 100 years ago was out in the country and is now located in the middle of the city, it's naturally going to show warmer temperatures. So that's one of the big effects that hasn't been taken into account adequately. I better stop. Oh, you got one more? Okay.
Thanks for coming out tonight. It's a blessing to have you here. I had two questions, actually. Do you believe that your simulations would explain flash freezing, like we see with the mammoths and stuff like that in Siberia?
No, I don't believe those. Well, I shouldn't say that completely. The question is, does this climate effect that I suggest explain flash freezing of mammoths? Generally, it's thought that mammoths would have had to have extremely cold temperatures to freeze and leave fresh or relatively fresh content in their stomach and in their teeth and so on. However, if you have an intensified storm with extremely strong winds producing cooling rapidly, you can have a blizzard that can produce a tremendous amount of cooling as well. So it's possible, and I've even suggested a mechanism for where that might happen, where many of the mammoths up in Siberia could have gotten frozen very quickly because of the intensification of the storms in that region. I have not adequately justified that, but I think that's probably an explanation for it.
And then just last question, sir. The pre-flood firmament, do you believe there's any possibility it was a solid sheet of ice?
The pre-flood firmament. Oh, no, I tend to reject the idea of an ice shell surrounding the Earth. The mechanics of keeping that ice shell there, relatively thin ice shell, would cause it to crack and fragment and fall out. So, and even if it were made, some have suggested a very strong material like solid hydrogen. And I think we're grasping at straws with that kind of an idea, so I don't accept that. I've been a long-term researcher on the vapor canopy, but I haven't been able to make it work either. So I've been frustrated for 30 years trying to understand what happened pre-flood and can explain it in conventional terms, and I haven't been able to do that. That's one big disappointment in my career. Sorry.
Thank you, Dr. Vardiman.